lecture we shall start the working stress method. We shall start this lecture with the working stress method. Before going to the before going to the different that your actual method, let me give you that one the different steps of construction, just one schematic one. I do not know whether you can see, can you see this one, just a floor, okay. So, there are these are all three different say footing, because I have told you the construction. So, three different footing, the other three and other three. So, there are say 9 column footings, and we are having say columns, the second level and third level. So, that we can have, and this is your that tie, these are all tie beams. So, we generally do not provide the, for wall we do not provide the wall footing, we start from this tie beam which will take the wall load. Also we can take it for the frame also, that connection, that also we consider, but we generally use it for say walls. And we have that beams, though we construct these beams and slab all together, whenever we cast these beams and slab that all together, but just to show you that otherwise I cannot show you, because if I keep that one the roof, then we cannot see the beam. That is why I have made it. So, this is the one actually the construction how we do it. We have started from the bottom, but when we shall design we do it other way, we start from the top. So, slab, then beam, then column, then tie, then footing. So, this is the one during the your design will be there. Even if you have staircase, the staircase has to be designed first, we do design is first. So, this is the just only one schematic one. So, I should acknowledge here, because that particular program, and that is your POBRE. The program name is POBRE. So, I have used that POBRE that one for this one. I thought okay, I shall use. This is a very free software, and I have found so far say so many softwares, rendering softwares available, but I have found this one is the so far the best one. Of course, my best thing always changes. That is another part. Anyway, so this one just to show you one example, you can also try. You can download and you can also try that different thing you can try. Okay. Yes. So just to name it, I think I should write down POV. RAY. So, working stress method we are talking, and we should have the limits. Direct tension, I could write down in PowerPoint, but then I find that it will be difficult. So, that is why let us write down in paper, so that you also can copy. So, grade of concrete, because these are the limits we should know. And tensile stress, we have M15, though we do not use it, but M15, and the permissible stress is 2.0 Newton per square millimeter. M20, 2.8, M25, 3.2, M30, 3.6. There are so many others, but we shall consider M15, M20, M25, M30. Generally, we consider RCC that M20 and M25. So, our tensile stresses 2, 2.8, 3.2, 3.6, and this is from page 80, IS 456, 2000. Let me write down from. So, this is your the limiting values for concrete when it is under direct tension. When it is under direct tension, so these are the limiting values, and we shall mainly consider these two. So, we could remember it also 2.8 and 3.2. Otherwise, of course, it will be specified in the that examination, that your question paper. So, I can go to the next one. I shall tell you. Because we should know the permissible stresses, otherwise we cannot design. Permissible stresses in concrete, and this one will be in Newton per square millimeter. And we shall specify again that 4 grades of concrete only. And permissible stresses in compression. Permissible stresses in compression has two parts. One is bending, another one direct. One is called bending, another one is called direct. The beam, when it is bent, that is called bending compression. The compressive stress whatever developed, that is called bending compression. A column, whenever you press the column, say like this, you are pressing the column like this, then that is called direct compression. So, you have that bending compression and you have direct compression, two different that the compression. And permissible stress in bond, and this one average. Also we can write down, to be more specific, for plain bars. And those will be in tension. So, permissible stress in bond average value for plain bars in tension. So, we shall write down the tension, and we have, we give it say sigma CBC, that is your in concrete bending compression, sigma Cc concrete direct compression, and tau Bd. For M15 it is 5.0, direct compression it is less, 0.6, M20 7.0, 5.0, 0.8, M25 8.5, 6.0, 0.9, M30 10.0, 8.0 and 1.0. This is, we have taken it from table 21, page 81, IS 456. You can see I have told that factor of safety about approximately 3. So, you can see 15 by 3, 20 by 3, which is coming approximately, which is coming the factor of safety 3. That means the cube strength here 15, 20, 25, 30, and you can get the corresponding bending compression in concrete almost 1/3. So, that means we are considering that factor of safety 3, that which I have told in the very beginning, that we are considering it here. Now, what about steel then? We have to consider for steel also. Let us give the permissible stresses in steel. So, permissible stresses permissible stresses in steel reinforcement. Type of steel, tension, compression, and we should have shear, because these are the different cases where you have to consider the permissible limits, or in other way that your freedom, that how far you can go. Fe 250, that is mild steel, Fe 250 is the mild steel. For that we have up to 20 millimeter dia, we have 140 in tension, 130 in compression and 140 in shear. Over 20 millimeter diameter, 130, 130 in compression and again 130 in shear. That means 130 for all of them, 130. Only in tension and shear it differs if the bar diameter less than equal to 20 millimeter. Fe 415, high yield strength deformed bar. high yield strength deformed bar HYSD, high yield strength deformed bar HYSD up to 20 millimeter, it is 230, 190, 230, over 20 millimeter, 230, 190, 230. And this one we have taken from table 22, page 82, IS 456, 2000. You can get it in this code, you can get these values, you can get these values in this code, but you should keep it in your exercise book also, because we require that one for our calculation. So these are the limiting values for concrete and for steel. Okay. So how shall we calculate the tensile stress? How shall we calculate the tensile stress? That again we can find out. The tensile stress equal to Ft divided by AC plus MAST, where Ft equal to total tension on the member minus pretension. This one we are talking that pretension, that I am coming to explain, if any. Pretension means actually that if you have any pretension and then you are applying the load, then you are getting the tensile stress will be increased. So that means you have initial value of tension, that way you can say. So that you have to, obviously you have to deduct it. And AC, cross sectional area of concrete, excluding any finishing material, excluding any finishing material and reinforcing steel. Only we are considering concrete. M, that modular ratio, M equal to that modular ratio, and AST, cross sectional area of reinforcing steel, to be more specific, in tension. So the tensile stress you can find out that Ft you have to get it, and you can find out that FT the total tension on the member minus pretension in steel if any. If the initial stress is there, tensile stress, that you have to deduct it. Area of AC means that concrete area, and obviously you should forget the finishing. Finishing means say you should not take the plastering. The concrete cover, whenever we consider the concrete cover, say even if you give that say your reinforcement bar, if you can see the reinforcement bar from the bottom after cast the beam or slab, if you provide the plastering, it does not mean that you are giving cover. That cover, that is your say finishing material, not the one, it is not part of the concrete. So that is why we are very specific that we are not considering any finishing material whatever you are using. M is the modular ratio, ES by EC that you can say, but our code does not take in that ratio, it takes in a different formula that we are coming next. And AST, that crossing area of reinforcing steel in tension. So
that is crossing area reinforcing steel of all the bars.
Yes, all the bars. We are considering that always we consider that way. Even if we provide the reinforcement that bars, so AST actually means that how many bars you are providing, the total area that you are considering. And we assume that one, we can say we assume that as I say as a total one, I can say I am coming next actually, let me continue and then I am coming next to your point. So what is modular ratio, that already we know, but still let me make it clear. So modular ratio M that is called modulus of elasticity of steel divided by modulus of elasticity of concrete, and that one let us write down ES by EC. We also write down that our code says M equal to 280 divided by 3 sigma CBC. So we do not take it from ES by EC. Instead of that, we use this formula. We should remember this, where sigma CBC, that concrete stress in bending compression in Newton per square millimeter. So we are not going to that ES by EC. Instead of that, we shall take this formula that, and on the basis of that we shall calculate M, how much we shall get. So that one we shall take say 280 by 3 sigma CBC, that we shall consider. So now we shall come to your point. Though we provide reinforcement, say like this, as many bars, how many bars, we provide say number of bars, but when you are considering say AST, whenever you are considering that AST, what we do, we can simply say like this, there is nothing wrong, simply we can say like this, that is the total number of bars, this one, as if that we can consider one plate also, because when we are considering that, so but that is at a particular point, and we generally consider that I have already told that effective cover. So effective cover, the thing is that if you design the beam, when you are going to design the beam, you do not know which bar you are going to provide, but you are calculating the area of steel. But at the time of calculating the area of steel or say effective depth, you need effective cover, and effective cover is nothing but that clear cover plus phi by 2 the diameter of the bar. So, here what we do, we assume certain diameter. So, based on our experience, say okay, this is the moment. So, we know that this bar will come, whether 12 millimeter or say 16 millimeter or 20 millimeter, which type of bar diameter will come, that we can assume that, because if you do not many, even if you do 5 or 6 examples and then with the different say moments, immediately you can understand that what type of bars will come, because you do not have, finally if you consider at the end of the day, you will find out you do not have really, you do not have any choice, much choice. That means say okay, 250 millimeter is the width of the beam and you take certain diameter depth, whether you will provide say 320 millimeter dia, 420 millimeter dia or 225. So, like that if you find few combination, you will find out that you do not have many choices, because whatever area of steel you can compute, because finally you have to provide certain regular number. You cannot provide something say 312.5 millimeter depth of the beam. You have to provide either say 300, 325, in that fashion only you have to provide at the say 1 inch, in that way you can say. So, when you have to provide that one, so that means you do not have much freedom. So, one can also do it that he can keep his all the beams, say possible beams ready, that moment of resistance, also the shear capacity he can keep ready, and immediately when you will get those say moment, okay, let us provide this one, let us provide this one. So, from the table itself we can find out, and we have actually one code also, that is that design aid, that SP16, that I have already told actually in the first class. So, from where also you can find out from the moment of resistance, calculate and provide the corresponding reinforcement, that area of steel, that also immediately you can compute. That way also your design also will be easier. What we shall do now, let us take one example. That we would like to find out a formula, and we are working on the working stress method. Working stress method. Let us provide just 2 bars. That depth, overall depth, we consider it as overall of depth. So, overall depth capital D, width B, effective depth small d, and strain is linear. So, epsilon CB, the strain in concrete in bending, that stress divided by modulus of elasticity, and epsilon ST, strain in steel, say FST divided by ES. This is our neutral axis. We should have the corresponding stress because since concrete does not take any tension, that is why I am not drawing the stress diagram here, because all the tensile forces will be taken care of by the steel only. So, this is your say T, so FST times AST, the stress developed in steel, that is FST times the AST, that we shall get it, and FCB. Let us say this one, the depth neutral axis, so this is x. X is the neutral axis from the top, neutral axis from the top, and this force will be at the centroid of this section. So, C equal to area of this triangle half FCB times x, and we have definite say width also, so B. Is it clear to you? So, we are considering the concrete, that compressive stress will be equal to the area of this triangle, and that one actually we can say this one, this is a wedge, triangular wedge type. That means this one having the along the depth also you will get it. So, half FCB times x or triangular prism, to be more specific. If we consider that one, that this is nothing but one right angled, that one prism, and that one we have to consider the volume, that one only will give you the compressive force. So, half FCB times x times the width of the beam, that is the total compressive force here, okay, and the tensile force, this one here, and this length, that is the lever arm. So, equilibrium, we have two equations. One we can consider here, that equilibrium of forces, after all it is a static case. So, equilibrium forces. So, tensile force equal to compressive force, that one should be there. So, equilibrium of horizontal forces. So, tensile force T equal to compressive force C. The lever arm we can consider this one as a Z equal to, we can write down one say fraction of say D. D is the effective depth. So, Z is nothing but obviously it will be certain fraction of effective depth, because this is the lever arm we are talking. So, it will be certain fraction of the effective depth. So, Z equal to ZD equal to D minus x by 3, this one x by 3, this portion. So, D minus x by 3 is your lever arm. So, this one will be equal to D effective depth minus x by 3, that one will be your lever arm, which again we can write down x, again we can write down as another parameter, say KD. I am assuming x is nothing but another fraction of the effective depth. We are considering everything in terms of say effective depth. So, another fraction say K. So, first one we have considered that j, another coefficient we are considering that particular one, say k. So jd is the one, the lever arm we can consider, and kd we can consider that one, that how much is, what is the your neutral axis, depth of the neutral axis, that we can find out as if that it is kd. We do not know k, neither we know k nor we know j, but we can write down in this way, which we can write down as d times 1 minus k by 3. So we can write down jd, that means j equal to nothing but 1 minus k by 3. So this is one important equation here, j equal to 1 minus k by 3. So effective depth we can calculate, and we can take a fraction that we have to find out. If we can find out either k, or if we can find out j, then obviously we can find out the other one also. So this is the one that we do it. So now come to the next one, that moment of resistance. What we can do, let us make it this way. We can do it, let us keep it like this, then it will be, I think, easier. So we are keeping this one, and then let us make it in this particular fashion. I think we can, so that we can get the that equation again. So moment of resistance, so that is the one we have to find out. M will be equal to T times JD. I can write down T times JD, which is nothing but FST times AST times JD. So moment of resistance, if we consider from the steel point of view, so T times JD will give me the moment of resistance. Also we can consider from the other part also, that C times JD. So we can also write down M equal to C times JD, which equals half FCB times B times X times JD. So we can write down, now we can take out this one, because this is simply little bit of arithmetic only. So we can now write down, so M equal to C times JD, which equals half FCB B, X is nothing but I have already told KD. Let me write down here, X equal to KD, Z equal to JD, J equal to 1 minus K by 3. Already we have done it, times JD. So we can write down half FCB K J B D square. So we can write down half FCB K J B D square. We can write down this one as R B D square. R is known as the moment factor. So, if you remember that in the very beginning of the third lecture, we started with some things at m by I equal to f by y. From there also we have got certain equation that 0.167 f bd square, that we have got it. So, similar fashion also here also you will find out we are getting the same type of relationship, that means 0.167 f, that whatever you got, and here we are getting say r. So, r bd square. So, this r is dependent on FCB and also it is dependent on K, it is dependent on J. So, we can find out that moment of resistance of a section, we can find out. If we can find out K and J also, we can find out, and if we can get the moment of resistance, and we can check the section whether it can take the load applied on that particular beam. So, that way that moment of resistance is very, very important. The other one we can consider that we can equate the tensile force and compression force. So, T equal to C. So, we can write down FST, stress in steel, times area of steel, that one equal to half FCB B KD. So, this is your corresponding, that your force, and here we are getting this one, the corresponding force in the steel, or we can write down AST by BD. We can take this B and D. So, AST by BD, which will just rearrange that one, half FCB by FST multiplied by K, or we can write down P, AST by BD is nothing but P equal to half FCB by FST times K. This P is called reinforcement index. So, this is reinforcement index. We can get it from their percentage of steel also, we can tell. From there also you can get the percentage of steel also, you can find out. Also we can get it here from this equation, FCB by FST will be equal to 2P by K. We can also get the rearrange the equation other way also we can get. So, we can get this equation and also we can rearrange this one the other way, we can also specify this equation. Because we need those things. So, we can write down the, here we have considered the strain is linear, plane section remains plane before and after bending, that assumption. Epsilon CB by epsilon ST equal to, we can write down FCB by EC divided by FST by ES, rearranging FCB by FST times ES by EC equal to FCB by FST times M. ES by EC is nothing but M, because that is the one modular ratio, and we can consider this working stress method is nothing but modular method also. So, ES by EC, because that is the one, the governing one in our whole design, that ES by EC, that modular ratio, that M. Epsilon CB by epsilon ST equal to epsilon CB by epsilon ST, that is equal to, just if we go back, yes. So, if I show you here epsilon CB by epsilon ST, that is equal to, this is your x, just if we come back, that is your x, and this part is d minus x, because that is the total depth d, and this one x, and this is d minus x. So, when we are getting this one, so we can write down epsilon CB by epsilon ST is nothing but x by dx, the similar triangle, equal to x is nothing but kd d minus kd equal to k by 1 minus k. Now, epsilon CB by epsilon ST equal to this one, FCB by FST times M. So, we can write down FCB by FST times M equal to k by 1 minus k. We can write down in other way, FST equal to M FCB times 1 minus k by k. Just rearranging the equation, we can write down FST equal to M FCB 1 minus k by k. That also we can write down. Okay. So, we shall almost we have finished. So, FCB by FST times M equal to k by 1 minus k, FCB by FST equal to 2p by k, that already we have done it. If you see, already we have done it, FCB by FST equal to 2p by k. Therefore, 2p by k multiplied by M equal to k 1 minus k, or twice MP 1 minus k equal to k square, or we can write down k square minus twice MP 1 minus k equal to 0. So, we can write down k square minus twice MP 1 minus k equal to 0. We can find out M. So, M equal to 280 by 3 sigma CBC, getting from the code. We have to choose one particular grade of concrete, maybe M20 grade of concrete. For that M20 grade of concrete, we can find out the corresponding sigma CBC, compressive stress in bending. From there we can find out that modular ratio M. If we can get M, what we have to find out that K. But if we know M, modular ratio, and if we know that percentage of steel, that area of steel you have provided, so from there you can find out the corresponding your that K. So, K if you can find out, then also you can find out J, and we can find out, then we can go for your say calculation of moment of resistance. So, we go in this way. So, we shall go with some problem in the next class, and then you will find out, and finally, we shall go to that limit state design, because I think we should know the working stress method also. At least you should know at least one example, because it is not possible for us within this time frame to go to both. And if you see that your Varghese book, you will find out it is given in the appendix, that appendix A, possibly appendix A, you will find out the working stress method. Okay. So, we shall conclude today. So, we shall meet in next class. Okay. Thank you.